Hello and welcome to my next video on actual quantum computers. The physical realization of quantum computers is very involved. First of all, we need to know what kind of quantum circuits we can build, what are the quantum algorithms that can be used, and quantum communication systems which are going to perform the carrying of information. Most importantly, we need to define a criterion for the actualization of quantum computers. Let us identify the conditions for quantum computation. First of all, the system must be capable of representing quantum information. Then, the system must be able to perform a universal family of unitary transformations. We should be able to prepare a fiducial initial state, and finally, of course, we should be able to measure the output result. Now let's get into the nitty-gritty of it. Quantum information representation. Quantum computation is based upon the transformation of quantum states. Quantum bits are two-level quantum systems, and they are the simplest elementary building blocks for a quantum computer. They provide a convenient labeling of pairs of states and their physical realizations. For example, if we want to represent the four states of a spin 3/2 particle, they go as ket m is equal to plus 3/2, ket m is equal to plus half, ket m is equal to minus half, and ket m is equal to minus 3/2. These states could be used to represent two qubits. Most importantly, for computation, the set of accessible states should be finite. Next comes the process of identifying what forms a good set of states. First, let us discuss what does not form a good set of states. Let us take the position coordinate x of a particle along a one-dimensional line. This does not generally form a good set of states. Why? Because even though the particle may be in some quantum state or a superposition of quantum states, x will have a continuous range of possibilities, so the Hilbert space is going to have infinite size. In the absence of noise, the capacity that this Hilbert space has of carrying information is also infinite. But actually this is unrealistic. In fact, the presence of noise always reduces the number of distinguishable states to a finite number. In a perfect world, entire texts of Shakespeare could be stored in and retrieved from the infinite number of digits in binary. But the world is never perfect. Noise reduces the infinite, the absolute to finitude, which, though desirable, gives rise to an undesirable effect, decoherence. A key concept in understanding the merit of a quantum system to be used as a quantum computer is the concept of noise. As I've mentioned, that quantum noise manifests as decoherence. Decoherence corrupts the evolution of a quantum system, defining the length of the longest possible quantum computation as tau q upon tau op, where tau q is the time for which a system remains quantum mechanically coherent, and tau op is the time it takes to perform elementary unitary transformations which involve at least two qubits. Continuing with decoherence, the two times mentioned above are actually related to each other in many systems, since they are both determined by the strength of coupling of the system to the external world. The table on the next page demonstrates that this ratio can vary over a surprisingly wide range. The table also provides valuable insight into implementable quantum systems. This table here represents crude estimates for decoherence times, operation times, and maximum number of operations that a quantum system can perform. If we look one example, nuclear spin, the operation time is between 10 to the power minus 3 to 10 to the power minus 6 seconds. The decoherence time is 10 to the power minus 2 to 10 to the power 8 seconds. And the operations that a quantum system can perform is really large. It goes from 10 to the power 5 to 10 to the power 14. Now, as opposed to say the ion trap, where tau q is 10 to the power minus 3, tau op is 10 to the power minus 14, and n op is 10 to the power 13. We will see in general that the number of operations that any quantum system under consideration that can perform is really large as compared to a classical computation system. And this is where the power of quantum computation lies. In spite of the large number of entries, only 3 fundamentally different qubit representations are actually realizable: spin, charge, and photon. Ion trap utilizes either fine or hyperfine transitions of the trapped atom, which correspond to electron and nuclear spin flips. The estimates for electron in gold and gallium arsenide and in quantum dots are given for a charge representation with an electrode or some confined area either containing an electron or not. In optical and microwave cavities, photons of frequencies from gigahertz to hundreds of terahertz populating different modes of cavities represent the qubit. However, these estimates are to be taken with a grain of salt, as they are meant to give some perspective only on a wide range of possibilities. That brings us to the end of physical realization of quantum computers. I hope I have been able to explain the basic facts to you quite well. See you in the next video. Thank you so much for your time.